My name is Sijie, and I'm, it's my honor to here to present uh, the latest update about like the integration between Pulsar and Flink. I'll probably just do a quick introduction about Pulsar. Before that, I'll introduce myself first. So currently, I'm the Pulsar PMC member. I'm also a PMC member of another project called Bookkeeper. Bookkeeper is the storage layer of Pulsar. Uh, I used to work for Twitter and was leading the whole like messaging platform. And before Twitter, I was at Yahoo. Right now, I'm running a startup called Stream Native, which is a commercial open source startup around Pulsar. And I'm interested in any like event streaming technology. So what's Pulsar? I guess a lot of people heard about Kafka before. It's in the same category. We usually like use one sentence to describe what is Pulsar. So from the user-facing interface, it's flexible pub-sub messaging. But to tell the difference, like how Pulsar is different from other pub-sub messaging, is the second sentence is it's backed by a durable log storage. And the sentence also tell the like the difference between Pulsar and from Pulsar to other like pub-sub messaging system. It's a two-layer architecture, and I'll show you later in the slides. So just give like a brief introduction about a brief history about Pulsar. The original idea of Pulsar was started around like 2012. It started from like I think it's from Yahoo Beijing Research Center. The idea was try to build a whole like Yahoo internal messaging cloud, and it has been running on production for more than 5 years. And it's serving like 100 applications and duplicate data over more than 10 data centers across the world within Yahoo. Around like 2016, September 2016, Yahoo open sourced the project and put it on Yahoo's GitHub. About like I would say 9 months later, Yahoo donated the project to Apache Software Foundation, and it gets into the incubator state. And we run the project in Apache Foundation for about a year. And September last year, Pulsar was graduated as a top level project. Right now, it has about like 25 committers from, I would say, 7 to 8 companies, and about like 154 contributors. Right now, we just passed like 4,000 stars, and it has close to 1,000 forks. And right now, it's adopt like in a lot of like companies from internet giants to gaming company, also some of the blockchain companies as well. Like for example, like the first 2 adopters, Yahoo Japan, and recently we have the Chinese internet giant Tencent adopt Pulsar for its core billing service for processing like tens of billions of transactions per day. So it means like every purchase you made in Tencent product, either gaming or like maybe like on WeChat, it all goes to Pulsar, and also some other companies as well. Initially, when we Yahoo open source Pulsar, it's mainly a pub-sub messaging. As what I said before, is a 2-layer architecture. So you have a messaging layer, you have a storage layer, and originally the storage, it was using Apache Bookkeeper. Bookkeeper was kind of incubated from Zookeeper. It basically brings all the log replication algorithm out of the dispute consensus algorithm and abstract it as a log storage. So then it can be reused for building other dispute replicate service. And Pulsar was originally built on top the Bookkeeper. And when we open source Pulsar, and when it, I would say, after it enter Apache Foundation, it get a lot of attractions, and adoption is increasing, and a lot of people start using Pulsar in different use case. I mean, one of the feature that Pulsar has is a unification of traditional queuing and also streaming. So a lot of people use in these traditional messaging scenarios, like a push notification, worker queue, and also it's used for like the streaming use case, like logging pipeline. And some of the companies try to use Pulsar as a unified event bus or event center to unify their existing, I would say, isolate messaging technology. And we see like increasing demand or like adoptions is coming from putting Pulsar and Flink together to building a streaming first unified data processing architecture. And that's what I'm going to talk today. After like we getting into Apache Incubator and graduate as a top level project, we add a lot of features into Pulsar, so it became more not just a Pulsar messaging, it became more like an event streaming platform. For example, in the storage layer, we introduced this concept called tier storage. So you can offload your like streaming data into much cheaper cloud native storage, like in cloud provider, you have S3, GCS, Azure Blob Store, and like in offline mode is you have there's a lot of deployment of HDFS. On the messaging part is we provide more language clients and also introduce a framework called Pulsar IO. So basically you can building connector to get data in and out of Pulsar. And we integrate with a lot of change data capture library like DBGM to capture the database changes and get the changes into Pulsar. In the data processing side, we integrate with a lot of like big data technology like Flink, Spark, Presto, Hive, and additionally, we bring in the serverless concept from cloud into messaging. We introduce a concept called Pulsar function. So you can write like a simple lightweight function to process the events as the events arrive. So this kind of new features we brought into Pulsar, like form the new like Pulsar 2.0, and all the features are kind of getting into more adoptions. Going back to the talk today is I'm mainly talking about how to use Pulsar in Flink to building like a streaming first unified data processing architecture. So that is fit into the category I just saying is how to use Pulsar for data processing. And let's take a look at a few like categories that we like use computing engine to do data processing. And the first category is you have these interactive workloads. Like you have a lot of data scientists, like users, they want to just write circle queries on your historical data or streaming data. Those queries are typically time sensitive and running on a medium size of data. And the fault-tolerant model is you rerun the queries on failures. You have the famous batch processing, like the whole Hadoop ecosystem is you are the amount of data you are going to process is huge, and the whole job is running in a huge clusters. And you provide a more fine-grained fault tolerance model, so you can rerun like the task on the split or on the partition. You don't need to rerun the whole job. And the most fast-growing category is the streaming. It's in the streaming world is most of the job is a long-running job, and it's real-time, time-sensitive. It requires both scalability and also the fault tolerance, because you don't want you want to process the data because the ingestion data can be increasing like a lot. So you need to have the scalability to process the data as the amount of the data ingested increase. And the last category is we see a lot of these use case like ETL transforming are kind of very lightweight processing, especially when increasing of the IoT area. You will have a lot of like these small edge data centers, and they do the raw data processing and send some simple field data to your cloud for more complicated data processing. So in this category, we call kind of a serverless use case is you want a very simple lightweight computing engine and to do this simple job like filtering, projection, maybe simple aggregation. So in a lot of this case, some of the, so for all the category of the data processing and Flink as a rising like computing engine is attempting to unify all the data processing in the computing layer. Is from Flink's view is all the computation is streaming first, and batch processing is just one of the special case, or like I would say bound stream processing of the stream processing. So that is the vision or the goal of Flink is going to like address. Similarly, in Pulsar, we have the same vision, but it's more from the data perspective, not from the computation perspective. In Pulsar, we treat the data as an infinity stream, segment streams. Basically, it means all your data is keep appending into streams, but it would never end. But the streams are truncated into segments. So in this way, you have two levels of API to accessing the data. Is one, you can use traditional PubSub mesh API to accessing data in streaming mode. Because the stream is truncated into segments, you get also fine-grained access to the segments within the streams. So what we call it's a segment API or a ledger API to access the data. So that is the view of how Pulsar views the streams. And because Flink is trying to introduce the unification on computation, we have the same view on the unification on data. So if you put Flink in Pulsar and Flink together, you're able to build like what we call streaming first unified data processing. And how does that mean is first you need to see why Pulsar fits in well in Flink. There's a lot of points, but I will probably just skip that. Is just like some marketing points. So the first kind of from architecture perspective, why Pulsar fits well into Flink is it uses a cloud native architecture. Different from traditional PubSub messaging is separate the serving from the storage into two layers. What does that mean is traditionally you only have one layer in the messaging system. What the layer is called broker. And both the messaging serving and also the message storage are happening in the same layer. In Pulsar, we kind of move the message storage out of the broker and use a scalable storage layer to keep the messaging data. The benefits of this multi-layer is the broker became stateless. What does that mean is that you don't actually store the data on the disk of brokers. So you can easily use any container technology to containerization the serving layer. So in the left side, I call it like stateless serving. It's basically each broker doesn't have store any data locally on the broker. That give the benefits is if any broker crash, you can easily start a new container and start serving the traffic. So you don't need to recopy the data when the broker crash. And also the other benefits is you have two layers. You can scale the layers independently. For example, if you want to store the data for much longer time, you just drop in more bookies, which is the storage node. If you want to serve more producer or consumers, you can just drop in new brokers. So you can do a better job on estimate all the capacity you need to use that for your storage, sorry, for your messaging data. So that is the first layer, and also because of the separation of the messaging serving and the storage, so it's allowed to provide the two layers of the accessing API. So you can access the brokers for Pulsar messaging. You can access the storage for more fine-grained like segment accesses. So that is the first point why Pulsar fit well into like the unified data processing architecture. The second there is similarly as most of the Pulsar messaging, you have the concept called topic, and the topic is partitioned into partitions. But a bit different is in Pulsar, the partition itself is a logical concept. So it doesn't belong to any like broker or any storage. And the partition is truncated into segments. And the segments is distributed and stored and replicated among the storage node. So you can evenly distribute all the data across the storage node. So when you want to store the data for much longer time, you can just simply drop in a new storage node. That means the size of the partition doesn't bound to any like the storage capacity of any brokers or like physical machines. So you can you are able to do you are able to store infinity like streams. So that is the second point. And because physically it's break down into segments, so it allows you to access the data in a fine-grained segments layer. So that is the second point, that when you want to build unified data processing, you are able to provide a different access points. And the last one is the common abstraction of Pulsar is an infinity streams. And the stream is break down into segments. The latest data is cached on brokers, and the segment is stored in the storage layer called Apache Bookkeeper. But we find if you want to do unified data processing, you want to keep the data for much longer duration, like for more than 7 days, like probably a month or even half a year. So you probably don't want to store like all the data in Bookkeeper. So you want to leverage existing like storage, like on cloud, you have a lot of scalable cloud native storage. On in data centers, you already have HDFS or those much cheaper storage. So in like I think 2.2, we introduced a concept called tier storage. What does tier storage mean is when you keep appending the data into streams, new segments were generated for the new data, but the old segments became older. So those old segments can be offloading into tier storage. But from users' perspective, you are still seeing this as a whole unified streams. You don't need to worry about where we store the segments. Other segments in Bookkeeper or other segments stored in S3. So this will provide a unified view of your data, and that is the third point of the unification. So getting into a bit detail about the whole like concept or the model within Pulsar is still, you have a topic. The topic is the entity for storing all the messages. You have a producer to producing data. You have consumers to consume the data. And the topic is break down into partitions. You can have as many partitions as you want. For each partition, it's physically it's break down into multiple segments, and the segments can be mapped into in Blob Store. It can be mapped into Blob in Blob Store, or you can store as a ledger in Bookkeeper. So this allows you to distribute the segments across your storage layer. So if you take the whole concept, the core value of Pulsar is an infinity streams infinity segmented streams. So you have like infinity append only streams, but it's segmented, and you are able to access individual segments as well. So that's what we see, like Pulsar is able to provide a unified view for your data. For the latest data, you can use the traditional Pulsar messaging to access the data in real time. And because the stream is break down into segments, so you are able to use the segment readers to access individual segments. And accessing individual segments is more close to the traditional batch processing model. So that is how Pulsar view the data, and how we think the unification view fits well into Flink's processing, Flink's vision, and also Flink's unification. And as I mentioned before, is you are able to have use two different APIs to accessing the data in the streams. One is in the streaming mode, you can use Pulsar messaging, is you have producer producing the data into the streams. You have the consumers or subscribers to consume the data out of the streams. Because it's a pen-only infinity streams, you are able to seek to any position and reprocessing data or backfill the data as just like a sequence access of the whole streams. Additionally, because the stream is segmented into multiple segments, so if you don't want to, if you don't need order, you want to more fine-grained parallelism for accessing the data, you can access individual segments via the segment reader. So you can process the segment as a batch for a given task. And because it's a pen-only stream, so right now we have a simple like publish time index of across the segments. So you can do a simple predicate push down to filter out all the segments you need for processing a given query. So that is the two different layers for accessing the data within Pulsar. And that's when you have a unified view of on data. So all the computation can be converted into either you process a bound streams, or you process an unbound streams. And I think that aligns very well with the Flink's process model. So that's why we see the combination of Flink and Pulsar can give a new value of how to unify data processing. So previous slides, I kind of give you an introduction of what is Pulsar and how Pulsar view the data, and what kind of interface Pulsar provides for accessing data. So when we bring Pulsar and Flink together to build the data processing, it's about how we want to integrate these two systems together. So I gave a talk in Flink Forward San Francisco like about a few months ago, talking about the integrations between Flink and Pulsar before. It's mainly, the integration was done on Flink 1.6, and the integration is mostly about using Pulsar as a source, as a sink, and how the data process can be applied to Pulsar. And I have a blog post on Flink website as well. If you want, you can check out that blog post as well. But the integration was kind of done very basically. It's because it doesn't fully leverage the features of Pulsar, and we kind of redo the integration, and it's integrated with the latest 1.9 Flink release. And the whole integration is all around a core concept called Pulsar Schema, which means we treat the Pulsar streams as a structured streams, and we leverage all the schema information that Pulsar already have. So you don't need to provide additional like a serializer or deserializer on Flink when processing the data. You just leverage all the schema information within Pulsar. And the second point is we make sure the Flink table API as the first class citizen. So you can register Pulsar streams as Flink tables in Flink jobs. So you can run Flink circle queries on Pulsar streams. You don't need to write additional Flink jobs. And the last two is related to the source in Sink, but we did the exactly one source. But Sink still at least once, but we are working on the exactly one Sink with transaction support, which I will talk later. So before that, I'll give you a brief introduction about the Pulsar schema, which I think it's the core of Pulsar right now. And also it's the core for bridging Flink in Pulsar. So a schema is the consensus of the master data in Pulsar at the server side. So you can think about it's a built-in schema registry. And the data schema is on a per topic basis. So every topic has a schema, and you can evolve the schema. And when you send the messages, you send a message, so type it messages with schema. And Pulsar broker would do all the validation to make sure your data meets the requirements or the format of the schema. And because the schema can be evolved, so so each message would be associated with a given schema. So it's a multi-version schema. So you can use the right schema to deserialize the data. So just give you a quick example. What does that mean in Pulsar API is traditionally you have a producer, you have a consumer, producer to produce the data, and consumer to consume the data. Most of the messaging system is you produce a chunk of bytes and you receive a chunk of bytes. But all the serialization and deserialization you have to done in the application layer. But right now in Pulsar is you just define like a POJO of your schema. Like in this example, it's called a user. When you construct a producer, you can specify, okay, this is our schema, and the schema definition is the structure of user. And when you send a message, you just send the POJO. You just send a user. You don't need to like serialize yourself into bytes and send bytes. And similarly, in the consumer side, is you construct the consumer with the same schema, and you receive the POJO. So you don't need to deal with how to serialize and deserialize the data. And this gives you an example of so each topic is associated with a schema. And the schema is stored as a struct called schema information. And the schema information, you can think about it's a JSON string, JSON struct. You have the field type indicating how to serialize and deserialize the data. In this example, it's a JSON schema. You have a second field called schema, the real schema. It defines like how many fields you have in this schema, and for each field, what is the type. And the last one is the properties. It's kind of user-defined properties, so you can put any information you want to store for associated with this schema. Because in a streaming system, all the structures of messages or events can be evolved. Like new fields would be 8. Some of the optional fields might be removed. So Pulsar will keep all the versions of different schema. So how does that work is, I'll give you an example how like producer, when producer connect to broker, how all this schema information is exchanged. So first, the application of provide a schema to the producer, and the producer would connect to broker and carry on the schema information. And the broker would check if the schema is already registered or associated with this topic. If it's already registered, you just return the schema version. And the producer would use the schema version to produce the messages. And each message produced by this schema will be attached with a schema version. So the consumer can use that schema version to find which schema to be used for deserializing the data. If it's not a registered schema, it would go through a compatibility check, like check if it meets the requirements of like backward, forward, or full compatibility. If it passed the check, it will register the schema. If it doesn't pass the check, it will reject the connection. So the producer will be dropped, and it's not you are not able to produce any data using this producer. So this is from producer side. Similarly, on the consumer side, it does the same logic. Is when a consumer connect to the broker, it will also do the same thing, check if the schema meets the requirements. So I'll probably just skip here. And as you see, on the streams, your data will keep evolving. Like new fields might be introduced, old fields might be deleted. So you need to have different compatibility check policy to check the schemas between versions. So originally we have this backward, forward, and full compatibility check. That means it only checked the schema with the previous version, but sometimes it's not enough. Is version 1, for example, version 1 might be backward compatible with version 0. Version 2 might be backward compatible with version 1, but sometimes version 2 isn't compatible with version 0. So in the latest release, we introduced a transitive strategy, compatibility strategy check. Is for any given new version of the schema, it checks all the compatibility with all the previous version. So it guarantees all the message data is either backward compatible or forward compatible or full compatible. So that is the compatibility check strategy. And on the consumer side, you also need to deal with the multi-version schemas. So in that way, is because each message produced by a given schema will be attached with the will be attached a schema version, and the schema version can be used by a consumer to identify which schema you need to use for deserialize the data. So this is the kind of a simple logic is how the consumer use the schema information. So when it receives a message, it get the schema version attached to the message. And locally on the consumer, it maintain a schema reader cache. So it will check if the reader cache has the given schema. If it has the schema, it use that schema reader to read to deserialize the message. If the reader doesn't exist in the cache, it would go back to the broker and look up the schema by the schema version. So it get the schema, it would initialize the schema reader for that given version and use that version to deserialize the data. So in that way, you can handle the deserialization correctly with the right schema information. So that is the schema. So the whole this multi-schema version and also backward compatibility are all managed by the Pulsar itself. So when we integrating Pulsar with Flink, the most natural way for us is mapping the a Pulsar message into a Flink row. In that way, you need to map the schema information into a row field. So for topics that without schema or with primitive schema, either you store the message data as integer, string, or any other primitive types, we just put the matched payload into a field called value. So it's a value in the Flink row. For the struct schema, like if you store a message in Avro format or JSON format, you get all the fields of that struct. And we map that struct, we keep the field name and type and mapping the field name and type to the Flink rows. Additionally, because each message you have multiple metadata fields like publish time, event time, you have the message key, you also have the topic information that which message is from. So this would become the metadata field in the Flink row. So just give you a quick example about the how we do the schema mapping. Is the right side is the primitive schema. In the example, I think it's the schema is the double. So you store a double number in as a message in Pulsar. So when we mapping Pulsar message into a Flink row, it will become the message payload would be the value, and all the message keys, topic, publish time, event time will become the metadata field. And the left side is an example of the structure schema, a struct schema. And this example is Avro schema. So you have a first struct is full and have 3 fields. One is integer, float, and a next struct is bar. And the bar also have 2 fields, is the B and S. So this is a struct with nested struct. So when we mapping the struct schema into Flink row is for the top level struct, we map the field directly. For any nested struct, we map we map the name with the for example in this example is the bar, and for referring the S field in bar is the bar.s. So in this way, we are kind of flatten out all the fields in the Avro struct. And so you can access individual fields in the Flink row. So that is the example of how we mapping the Pulsar messages with schema into a Flink row. So based on this information, so we built a new source connector. Is right now you don't need to specify what is your type of for the Flink job, because all the message will be converted into Flink row. So you can just define a source and providing the properties, how to connect into Pulsar and which topic to read. So in that way, all the Flink source would return the individual Flink rows, so you can process the data there. You can also register the Flink, Pulsar streams as the streaming tables in Flink. So basically, you use this streaming environment. You can connect to a Pulsar definition, like what is the Pulsar cluster and what topic you are going to map. And you can register that Pulsar topic as a table source. In that way, it will return a table in this code, so you can access the run all the computing job on that table. To point out here is we haven't provide like a Pulsar catalog in Flink. If we provide a catalog in Flink, you don't actually need to register the table source. You can just connect to you can just define how you want to connect Flink to Pulsar, and all the Pulsar became a catalog in Flink. So you can just select the table or like write the table back to Pulsar. So how did we do? How did we implement the Pulsar source? Is basically for individual topic we have so for the Pulsar source, you specify a topic or a list of topics. It will start a topic partition discover. It will discover what are the the list of topic to consume. And for each topic, it discusses any updates of the list of partitions. And for each partition, it will start a reader, and a reader would use the Pulsar schema for us the deserializer. So it deserializes using the Pulsar schema information. And that is the source part. And to achieve exactly once is because Pulsar, each partition is an infinity like streams. So you can actually, you process the data in the partition order, and you can seek and rewind the read to a given point. So when we implement the source, we like store the checkpoint with the message ID. So when it crashes, it can recover from the checkpoint and restart from the given message ID. But one of the challenging you have to do here is because Pulsar is a subscription-based system, so all the data we have to be keep alive for a given subscription. So we don't acknowledge or like move the cursor when we finish a checkpoint on individual source tasks. We only checkpoint, or we only move the cursor when Flink tells that a checkpoint is fully complete. So in this way, we can guarantee all the data needed by Flink checkpoints are retained until they finish the checkpoint. And the last one is about a Sink. Sink is similar. Is you can still, you don't need to specify any like type of information. In the use the Pulsar schema information. You can also register a Pulsar topic as a streaming table. So in this example is you can register the testing topic as the table, costing table in Flink. And when you execute a Flink circle, you can insert the updates back to Pulsar. So in this way, so all the Flink integration are done around the Pulsar schema. So you use Pulsar schema to managing all the data. So you don't need additional like schema information or external schema information. But this is the first step that we want to like fully like integrate Pulsar and Flink. But there's still a lot of work to do. Like for example, in this example, so in the previous integration, we do the batch sync, but we didn't do the batch source and batch sync in this integration. Is we are waiting for the Flip 27, the Flink community's attempts to unify the source API for both batch and streaming execution. So we don't want to like introduce a batch source or batch sync. When the new API come out, we have to redo the integration again. The second one is right now you have to register like individual topic as the tables, but we want to fully integrate Pulsar and Flink and let Flink use Pulsar as a catalog. So you don't need to specifically write, okay, I want to register this topic as a Flink table. And the last three is mostly about like we want to fully use all the potentials in Flink in Pulsar, like use Pulsar as a state backend, and we also want to scale out the source parallelism, like by leveraging the new subscription type called key shared in Pulsar. And in 2.5, Pulsar 2.5 release, we are going to introduce Pulsar transactions. So we want to use Pulsar transaction to implement exactly one's Flink sync. So we are able to make sure end-to-end exactly ones from like across multiple Flink jobs. So I'll probably just skip this. And conclusion is Pulsar is a kind of a new messaging system. It's a multi-layer architecture to combine both messaging and storage. And it provides two layers for accessing data. You can use Pulsar messaging for accessing streaming data. You can use segment reader to access more fine-grained segments. And Pulsar attempts to provide a unified view for your historical data in real-time data in infinity streams. And Flink attempts to provide a unified view for computation, and the combination of two can create a streaming first unified data processing architecture. And this is the kind of the end goal we want to achieve is a better integration story between Flink and Pulsar for simplify the whole data processing use case. And lastly, this is all the community information. So if you are interested in Pulsar project, you can use these links for accessing documentation, user stories, or blog posts about Pulsar.